Hello, my fabulous chemistry students. Video 4, building stable compounds. We are going to use these pesky oxidation numbers, which are in the top right-hand corner, to figure out how many of each atom I need to get a stable compound. Okay, so where do we get them from? Well, we get them from the periodic table, and they have to equal 0 when we're done. One of the other things we're going to be able to do today is figure out what a polyatomic ion is. Okay, and here's an example of one. And table E is a list of them with their names. If you get some funny names, you're not really sure what it is just by the name. The saying goes like this: when in doubt, check E out. Okay, each element within a group has its own charge or oxidation number. These are these up in the right hand side, and we're going to find that the top one is usually the one we use the most. There will, of course, be some exceptions, especially for the transition metals. So, number one rule, if I'm all by myself, I have an oxidation number of 0. So just sodium metal has got an oxidation number of 0. Okay, diatomics, oxidation number of 0 because they're all by themselves. Okay, but now when we start getting into compounds, this is where things are going to start to get a little interesting. I need to combine their positive and negative charges so that I equal 0 total. Okay, so here's some examples. Na, if I look up Na's oxidation number, I have a +1 and chlorine is a -1. Well, 1 plus -1 is 0. We good. Magnesium and nitrogen. If I look up magnesium, I have a +2 charge, but I have 3 of them. So I have to multiply that by the 3. So 2 times 3 is a +6 total charge for magnesium. I know that then my total nitrogen charge must equal -6, excuse me, so that I get to my 0. But now I have to go backwards. So backwards from multiplication is division. -6 divided by 2 is -3. So those are my oxidation numbers for those elements. Let's do one more, just because this one's even a little bit more complicated. Here, this is a polyatomic ion. I know this because I see it way too much. You guys have got to start getting a little bit used to table E, and you'll get it too. Hydrogen is a +1, so nitrate is going to be a -1. Okay, and so if its charge is a -1, we're going to find that instead of it equaling 0, it's going to equal -1. And we're going to get into that just a little bit later in the notes, and I'll do an example there so we can just speed this up and keep moving along. Some more rules. We always write the positive first and the negative last. So an example, HCl. H is positive, chlorine's negative. There's only one exception to this rule, and that is NH3. And it's got me kind of curious that NH3 could be positive and negative like this also. So we got to do a little bit of hunting to figure out if this is true or not. So there's your Easter egg for the day, Mr. Milks. Remind Mr. Milks to double check the oxidation states of nitrogen and hydrogen in ammonia. Okay. Group 1 metals are always going to have an oxidation number of 1. And guess what? Group 2 metals will always have an oxidation number of 2. So that'll help. And they don't have any choices other than those when you look on the periodic table. So I'm not going to go ahead and fill those ones in. Okay, if you got a +1, then you know what the other one's got to be. Fluorine is always a -1. And as a matter of fact, all the halogens will be -1. So right off the bat, -1, this has got to be a +1. -1, +1. -1, +1. I can assign -1s to these real fast because I recognize them as halogens, which is from last unit. Hydrogen is basically always a +1, except for when it is at the end of a formula, it's -1. And that is very rare that we get LiH. It's usually HCl or H2SO4. It's usually at the beginning. So it's just enough, just so you understand that there are some exceptions. Oxygen is almost religiously a -2. There is, one exception. When it's combined with fluorine, it becomes a +2. This one you will almost never see. The other exception is this peroxide, which is a polyatomic ion, where I have the 2 oxygens at the end, the O2. That's a peroxide. And we'll find that oxygen has a -1 then. But it's not even listed as a possibility on our periodic table. It is a major exception. You very rarely will see an exception like that, but I have to tell you about it. The only other difference now is the ions. So if I am an ion, where here I see this chromate, Cr2O7 is called chromate. It has a -2 charge. I can look it up in table E, and that'll give me its name. But so now basically the rule is I need to find the oxidation numbers of the two with their total being -2 now, not -1. Well, if I look up chromate, I have a +2, a +3, and a +6 to put in there as possibilities, right? And Mr. Milks did say the first charge is usually the charge, but we just don't know. I know oxygen is a -2. Well, if I have 7 -2s, that multiply those down, that is a -14. And I know now instead of equaling 2, I'm going to equal -2. I'm sorry, instead of equaling 0, I will equal -2. So what -14 is -2? Well, that would be 12. Right? Now I got to go backwards. So instead of multiplying, I divide. I'm going to say 12 divided by 2 is 6. So chromium is going to have a +6 charge times 12 equals, I'm sorry, I misspoke, times 2. Mr. Milks getting tired, equals 12. And then I have oxygen at a -2 times 7 is -14. 12 plus a -14 is -2, and that's what I'm looking for. So we're good. I assigned my oxidation numbers quickly and accurately. One common question that we're always going to come across: hey, which of these following compounds has both an ionic and a covalent compound in it? You're looking for a polyatomic ion within it. Let me give you a quick example. NO3 is nitrate, and a lot of times it's bonded with, say, something like silver nitrate. Well, we know we have an ion here at a +1 and an ion here, a polyatomic ion at a -1. So when the two ions hook up, I have an ionic bond. What the difference is down here. This N and the O3 were bonded previously, and it's two nonmetals. This is covalent. So the only time I can really have an ionic and covalent bond within the same compound is when I have a polyatomic ion. I love those questions. So here we go. Now let's identify some. Let's use table E. In table E, look up NH4 and tell me, do you find it? And if you do, write its name here. And then I want you to look up PO4 and tell me, do you find it? And if you do, I also want you to write that one there. NaH, do you find it? What about CO3? Or HCO3, can you find any of those? This one's cut pretty good. NH4 and NO3. We already found NH4. Okay, so I want you to look those bad boys up and write in their names, okay? The oxidation number of oxygen, of course, is always -2, except, in our peroxides, which we see the most as far as our exceptions. Therefore, in this case, hydrogen has to have a charge of. Well, let's see, I have -2, so oxygen is -2. -2 times 1 is a -2. Plus what gets me to -1? Well, +1, and hydrogen's a +1. Okay, it's got to add up to a total -1 charge because I see this negative right there. Okay, PO4 with a -3 charge. Well, the oxidation number in oxygen is usually -2. I have 4 of them, so it's going to be 4 times -2 equals -8. So now I got to back calculate. I have a total charge. I'm going to rewrite this, PO4 to the -3. I have a -2 charge on my oxygen. -2 times the 4 goes to -8. Well, I know that this -3 is going to come down here to be my overall charge. So what -8 is -3? Think. 5. 5 divided by the 1 coefficient, 5 divided by 1 is 5. Phosphorus will now have a +5 charge. I know I did it fast. You guys are going to need to do it over and over and over again so that we get it good. I guess we're going to need a lot of practice. So 10-minute video. Sorry we ran over, but this is some important stuff. We're going to be using it honestly well past Christmas over and over and over again. It's going to come into play so much. It's not even funny. We can use table E and find our formula charges, our polyatomic ions. We know how to build compounds now so that their overall charge is neutral. You guys have a great day, and I'll see you tomorrow in class.